Hello, I would like to welcome you to Lecture 13 of 3N03. We'll continue our discussion of applications for operational amplifiers. Last lecture we covered comparators, we covered summers, we covered analog to digital converters. In this lecture we're going to be covering digital to analog converters, integrators, differentiators, and then we'll show some examples. Okay, so in lecture 12, we saw how to build an analog to digital converter. We used, for 3 bits, we used 8 op-amps to compare against 8 different voltage levels, and then we're able to create binary output. In this circuit, the circuit I'm showing you here, this is a digital to analog converter. So what you do, you apply a digital word here. We have 4 bits, D0, D1, D2, and D3. Each one of these bits can be either logic 0, which we can take it as 0 volts, or it's logic 1, which we can take it as 5 volts or 9 volts, depending on the logic definition we define. But all of these bits, they are either logic 0 or logic 1, D0, D1, D2, and D3. So these 4 bits, they can count from 0, 0, 0, which is correspond to the decimal number 0, up to 1, 1, 1, 1. 1 here will correspond to e to the power 3. This is 2 to the power 3. This is 2 to the power 2. This is 2 to the power 1, and this 2 to the power 0. So you get 8 plus 4 plus 2 plus 1 correspond to 15. So our target here is once these 4 binary digits start to count from 0, 0, 0, 0 up to 1, 1, 1, 1. So these are 16 binary numbers. The output here will start to increase accordingly. So the output follows the input. There may be some phase inversion, but the output will follow the input. The gain of this circuit, as I will show you, this is simply an inverting amplifier, but these weights, the weights of these resistors, the 2R, 2R, and R and 2R, R and 2R, are being adjusted to guarantee a certain value, a certain input resistance value, and certain Thevenin value for each one of these voltages. So I will show you that through an example, but what is happening here is that for every applied voltage, you can try to use Thevenin equivalent. So for example, if I make D0 equal to 1, logic 1, meaning say it's 5 volts, I can use Thevenin equivalent to replace all this part to the left by a Thevenin equivalent. So I can replace this one by a voltage source in series with a resistor, and this resistor becomes in series with R. And then I come again at the next point, which is say this point here, and then I do a second Thevenin equivalent, and then this will, so all this circuit to the left of this plane, all this circuit will be replaced by a Thevenin voltage source and the resistor, and then I repeat the same here and here. Okay, at the end you will see that the resistance seen at this point is simply equal to 2R, so it's equal to this one. And you will see, depending on whether D0 is 1 or D1 is 1, D2 is 1 or D3 is 1, the equivalent Thevenin voltage scales up. So here it's going to be V reference over 16. So if you apply, say, voltage here of V reference, the Thevenin voltage seen at this point is V reference over 16. If you make this one only high, so this one is logic 1, it is V reference, it is 9 volts or 5 volts, whatever, and all the other 3 digits are zeros, you will see that what's seen here is a voltage source of value Vref over 8. This one will give you Vref over 4, this one will give you Vref over 2, and so on. So you can see they give you different weights depending on the position, and as a result the output scales, it increases by increasing the binary count of these 4 digits. So I kept this slide empty so that I can show you how we do the calculation for one of them. Let's say we'll make D0 equal to 5 volts, or let's call it Vref. Okay, let's call D0 equal to Vref. Okay, so and all the others are really ground. So this is gonna be ground here, this is ground here, this is ground here, and you can repeat the same for all of them. Okay, now the Thevenin equivalent seen at this point, you will see that you have two resistors in parallel, 2R and 2R. Then the Thevenin equivalent is simply equal resistance equal to R. And here you have Vref, but this now is open circuit, so you have a voltage divider, so you have 2R and 2R. So what is seen here is half of Vref. So I can simply replace, I can redraw the circuit here from this point here. I can replace this part from this point here by a resistor of value R and a voltage source of Vref over 2. Okay, this is what I can see from here. Now this R is in series with this R, so this will give me 2R. Okay, and these 2R, and then you have this Vref over 2. So if I try to apply Thevenin voltage again, Thevenin equivalent again at this point, you will see that you have 2R here in parallel with R plus R. So again, it will give you an equivalent resistance of R. And because these 2R and these 2R will act as a voltage divider, you get Vref over 4. So looking at this point, at this specific point here, this is actually what I'm going to be seeing. I'm going to be seeing a resistance R and then a voltage of Vref over 4. Okay? So now we repeat the same thing again. You have R in series with another R, then you get 2R. And then parallel with these 2R, then the equivalent Thevenin looking into this circuit from this side is simply equal to R. And so on. You do this over and over again until you reach the source. And when you do that, you will see that the resistance seen from this side is simply equal to 2R. So this point is connected really to 2R. And the voltage, because this one is only high, Vref over 16. Okay, let's take a look at an example. It's easier to illustrate through an example. So here we have, this is a 4-digit digital to analog converter. So as we agreed, as these digits start to count from 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, and so on up to 1, 1, 1, 1. These are 16 binary numbers. As these numbers count like that, the output will actually start to go down gradually and slowly to a maximum negative value. Okay, and the reason that's going down for a negative value because this one here has a negative gain. It's an inverting amplifier. So here we are using actually a practical amplifier. It's very famous OpAmp. It's called 741. It accepts dual supply 15 and minus 15 volts. This one is 2K, and here this is called an R2R ladder circuit. So this is 1K. This is 2K, 1K, 2K, 1K, 2K, 1K, 2K, and this one is 2K. So now we'll assume that D0 is equal to 1, is logic 1, so it's high, logic 1. And this means that it's set to Vref. Vref here I took it to be equal to 8 volts. And all the other binary bits have a value of 0. Logic 0, this logic 0, and this logic 0 will correspond by definition to 0 volts. So I would like to analyze this circuit, and again, what you will do, you will connect here Vref here, which is equal to 8 volts, and you connect this one, and this one to ground. And you'd like to see what you're going to be seeing here at the output. Okay, so this is what I did. I connected here Vref. These three are connected to the output. I removed the OpAmp. I removed the OpAmp itself because I don't want to keep on drawing it again, but the OpAmp is here, and this point will be connected to the negative terminal of the OpAmp. Okay, so looking into this side, I would like to get the Thevenin equivalent. If I ground Vref, if I ground the supply, I get 2K in parallel with 2K. Then the equivalent resistance is simply 1K. And here, because if I make this one open circuit, I'll see that Vref in series with 2K, in series with 2K, but these two act as a voltage divider. Then what I see at this point is simply half Vref. So I now redraw the circuit. After I put the Thevenin equivalent, so it's 1K and Vref over 2. Now, 2K and 2K, 1K and 1K will give you 2K. Now we try to obtain the Thevenin equivalent again, looking at this terminal here. If you look at this terminal here, you get the 2K in parallel with 2K, so this will give you again a Thevenin resistance of 1K. Now, if you make this one open circuit and you try to see the voltage at this point, the voltage is a voltage divider, 2K and 2K. So what you see here is Vref over 4. So you can replace this whole part here by 1K in series with Vref over 4. And this is what I did here. So you can see I replaced all this circuit by 1K in series Vref over 4. And this is within series with another 1K resistor in parallel with another 2K resistor. Now looking at this point, we repeat exactly the same thing. The Thevenin equivalent resistance is simply 2K in parallel with 2K, you get 1K. The voltage seen from this point is 1/2 of this voltage, then you get Vref over 8. So this is how the circuit looks like. Now, finally, to see the resistance seen, before we connect this to the op-amp, the resistance seen from here is 2K and 2K, so this will give me 1K, and this becomes Vref over 16. And if you remember, I believe there was another resistor connecting to the negative terminal. So this one there will be another resistor there. So let's take a look at the next slide, see how we can integrate this one with the op-amp circuit. Yeah, so what we did, all this part, what we managed to calculate so far, we got the Thevenin equivalent for this whole part. So we had large number of connections here in this part, we removed them and replaced them by 1K in series by Vref over 16. So this now looks like an inverting amplifier. I have 2K and I have another 2K. It's an inverting amplifier of gain of -1, because the gain of the inverting amplifier is V out over Vn is equal to minus 2K over 2K, so it's -1. So V output will be equal to minus Vref over 16. Remember, Vref is equal to minus 8 volts, so divide to get minus half volts. Now, what if we started by D1? If you made D1 is the one that's logic 1 and all the other 3 bits are logic 0. What you're going to be getting here is minus Vref over 8. So it will give you double the voltage of the least significant bit. What if we make D2? D2 to be equal to logic 1 or is equal to 8 volts and all the other 3 bits equal to 0. You'll get here minus Vref over 4. What if it's D3? You get D3 will give you Vref over 2. And so on. So you can see this one gives a higher voltage. This one gives a higher voltage than this one, than this one, than D0. Okay? So if they start to count from 0, 0, 0, 0 up to 1, 1, 1, 1, you will see that the output will start to increase gradually and slowly from 0. Actually, it's increasing in value, but it's negative in number. So it's going from 0, 0, 0 up to a maximum number that you can get here. Okay? And this maximum number is simply equal to Vref over 16 plus Vref over 8 plus Vref over 4 plus Vref over 2 multiplied with a negative sign. Okay, so I would like you to repeat these same steps when D1 is logic 1 only, and when D2 is logic 1 only, and again when D3 is the only bit was logic 1 with 8 volts. I would like you to repeat these same steps again yourself to see that indeed this is the case. And of course superposition applies. So when you have more than one bit at logic 1, then superposition applies, and then the output will be the sum of all these outputs. Okay, one of the useful applications of op-amp circuits also to create an integrator. An integrator is nothing really but an inverting amplifier where you put a capacitor in the feedback network. How we prove that this is an integrator? It's very simple. For any filter circuit, we consider this as Z2 of S or Z2, and this one as Z1. So we have Z2 and we have Z1. And for a circuit like this one, you say that V out over Vn is simply equal to minus Z2 over Z1, where this is Z2 and this is Z1. You can have whatever you want to have there. You can have inductors, you can have capacitors, whatever the case may be. Okay, so Z2 is simply minus, it's 1 over J omega C. I'm going to write it as 1 over SC. And you know from the lectures that S is equal to J omega. So I'm going to write this one as V out over Vn is equal to minus 1 over SC, and then you divide by Z2 over R, so it becomes 1 over R. So this will lead us to the expression that that minus CR S V out is equal to Vn. Or you know from phasor analysis, when you multiply by s and the s is j omega in the frequency domain, this is equivalent to the derivative. So I can take this one back to the time domain. These are all phasors now because I have s and the s is j omega. If I take it back to the time domain, I can write this one that this expression here is equivalent to that v out dot is equal to minus 1 over RC Vn, or if I integrate both sides, that V out is simply equal minus 1 over RC multiplied by the integral of Vn. So you can now prove that this is really indeed an integrator, because you integrated both sides here. So the integral of V out will give you V out, the integral of Vn, you simply doing out the integral. So the output of this circuit is simply the integral of the input. So I did the analysis in the frequency domain, in the phasor domain, as you could see here. But then I took the final result in the time domain. I replaced S V out by V out dot, the time derivative of V out. Okay, so when you do that, this is the equation governing this circuit, that the derivative of V out is equal to minus 1 over RCVN, or if I integrate both sides, that the output is simply the integral of Vn. There is one problem with the OpAmp circuit, the ideal OpAmp circuit integrator I've shown you, is that at DC, when you have a DC, this capacitor represents open circuit. So there is no, for the ideal integrator I've shown you earlier, there is no such resistance here. If this is an open circuit, this means there is no feedback from the output to the input. So any voltage that you apply here will cause the negative terminal of the op-amp to be higher in voltage than the positive terminal, which is kept at 0. There is no feedback anymore. So if these two are not there, then this means that the input, the negative input, can have a higher voltage than the positive, and that causes the output to saturate, and actually causes this capacitor to start to accumulate charges. So to remove this problem, what they came up with a practical integrator excuse me, a solution by putting this very high resistance in parallel with C. When you put this very high resistance, you are still guaranteeing there is a feedback even at DC, and this feedback will create will guarantee that you don't have this open circuit the open circuit loop, or the feedback loop, is not being broken, and this will avoid the problem of saturation, that the output is not going to saturate. So this is one practical approach. We put very big resistance here in parallel with C. So now I will show you why this very big resistance is good in avoiding this problem. Okay, so I intentionally redrew this circuit again with an empty space so that I can show you step by step how to do the analysis of this one, and this is very similar to one of the examples we had in the quiz. So this now is what I call Z2, and this is what I call Z1. So V out over Vn, it's an inverting amplifier, is equal to minus Z2 over Z1. So this is what you have to write here. So I can simply write that V out over Vn itself is equal to minus Z2 over Z1. Okay, what is Z2? Z2 is simply the resistor in parallel with the capacitor. So I can simply write this one in a little bit more compact form here. So I can simply write this one as minus 1 over we'll have now to put these two in parallel. So 1 over RF plus SC, and this is all divided by Z1, which is R, divided by R. Okay, now if I simplify things and I multiply both sides by this, I can take this R here, R in the denominator. Okay, I can take this R and then move it to here, so it becomes R over RF, and then the other one becomes SCR. Then I can simplify things in this form here, that V out over Vn is equal to minus 1 over R over RF plus SCR. Okay, now if you multiply both sides by by the denominator and denominator. So Vn will be multiplied by -1, V output will be multiplied by this one. And then I will take it back to the time domain. So R over Rf multiplied by the phasor of V out becomes R over Rf multiplied by V out of t. SCR multiplied by V out becomes CR multiplied by V out dot. So now I can write this equation in this form, that CR V out dot plus R over RF V out is equal to minus Vn. This expression is identical to the one that we had for the ideal integrator, where this resistor was not there, but we have this error term. This is an error term. It's related to V out. If this term is not there, then VCR V out dot is equal to minus Vn, or V out is simply the integral of Vn. But this is why if I select RF to be way bigger than R, then R over RF will be a very small number, then this term will be negligible relative to this one, and then it's essentially an integrator. And this is what we do. Usually you select RF to be a very large number so that the calculation will not be affected by their presence, okay? So what I did, I wrote the expression for this one. I took it back to the time domain. I have seen that this term represents an error. In order to get rid of this error, I will make RF way bigger than R. So R is much smaller than RF, so this term is negligible, and indeed V out is equal again to -1 over RC multiplied by the integral of Vn. Okay, let's take a look at an example. We have here an ideal integrator circuit. We have a 1 microfarad capacitor here. We have a 1 kilo ohm resistor, and then I apply to this circuit here. I apply a square wave. It has an amplitude of 1 volts, and it takes 20 milliseconds to complete one cycle. And I would like to determine V out. The trick part here, or the idea here, is that if you have 1 volts applied here, then there is a constant current flowing in this one, in this resistor. Where would this constant current go? It will be used to charge the capacitor. So when you have a positive voltage, this positive voltage will result in a positive current, okay? So it will result in this positive current, and this positive current will result in the capacitor. So the capacitor charges this way, and this, because this is a virtual ground, will result in negative output voltage. So the output becomes negative, okay? Now, if you apply a negative voltage like this one, the current will reverse direction. Then the current flowing from the capacitor will reverse direction. Then the capacitor is actually discharging, okay? So it will start to discharge back to its original value, okay? So the tricky part here, or the important part to remember, is that the capacitor is charging under constant current. When you have this 1 volts in this part, it's a constant current. And when a capacitor charged under a constant current, I will show you in a second that the voltage increases linearly with time. We have seen before that if it's charging through a battery, a voltage source, it charges exponentially. Here, when it's charging through a current source or a constant current, it charges linearly. Okay, so let's take a look at this one. Just keep in mind that this current will be flowing into the capacitor, will be used to charge the capacitor, and then in the negative part, this current will be flowing this way, so the current is flowing out from the capacitor, and the capacitor is discharged. Okay, so this is what we have here. The output voltage is equal to minus the capacitor voltage, assuming the polarity plus and minus. The capacitor voltage is equal, by definition, is 1 over C, the integral of I dt. The current flowing into the capacitor here is constant, and we call it here, we give it the value I, so I can take it out from this integral. And the integral of dt will give you time. This is why I told you that the capacitor voltage is increasing linearly with time. So the output voltage is decreasing linearly with time, because they are related through a negative sign. This is time here, t. And this is the capacitor. Now, what is this current? We agreed that we have a voltage of 1 volt, and the input resistance 1K, so it's 1 over 1K. Time, it takes first 10 milliseconds to charge the capacitor, so I multiply here by 10 to the minus 10 by 10 to the power minus 3, and then I divide by the capacitor value, which is equal to 1 microfarad. So if you calculate when you apply this positive voltage here, a positive current will flow and then it will be used to charge the capacitor, and then the output will start to drop, and you will see the value of the negative voltage that you get is minus 10 volts. Now when we repeat the cycle again, so we apply the negative voltage, the current will flow in the opposite direction, and then you can show very easily that the capacitor will start to lose its charge, and because it charged here linearly through the first 10 milliseconds, it discharged linearly also through the other 10 milliseconds, so it will go to zero again. So this circuit creates for you a triangular waveform that oscillates between 0 and minus 10 volts, like that. Okay, the capacitor is charging and the capacitor is discharging, charging and discharging. And remember, the negative sign indicates here that the output of the output is negative the voltage of the capacitor. An op-amp can also be used as a differentiator. This is a very simple differentiator circuit. This is again, it's an inverting amplifier. This is Z1 and this is Z2. So V out over Vn is equal to minus Z2 over Z1. So V out over Vn is minus Z2 over Z1. So if you calculate, if you do this here, very simple, you'll be able to get the expression V out over Vn is equal to minus Z2 over Z1. Remember that Z2 is simply R, and remember that Z1 is 1 over SC. So if you simplify, you get that V out over Vn is equal to minus SCR. Or if you multiply both sides here by this one, and you take into account that multiplying a phasor by S, which is J omega, is equivalent to differentiation, you get the expression, the time domain, that V out of T is equal to minus CR multiplied by Vn of T. So Vn dot of T. So here you can see that the output is the derivative of the input. Okay, the output is the derivative of the input. Of course, the negative sign, we can get rid of that by using an inverting amplifier, just a phase difference. We can get rid of that through an inverting amplifier. Now, this circuit has one drawback. At very high frequency, usually in every circuit, in every voltage, there is some noise, and this noise has very high frequency. At very high frequency, a capacitor tends to be close to short circuit. So this makes the ratio minus Z2 over Z1 to be extremely high. In other words, this circuit has the bad thing that it amplifies noise. It amplifies noise because for the noise where the frequency is very high, the capacitor will be effectively short circuit. Maybe it's 1 ohm or 2 ohms. So you are dividing maybe 2 kilo ohm by 2 ohm, then you are getting really again a very high gain. This is something, it's completely undesirable. So in order to overcome that, they put a resistor here, and this resistor is usually selected to be small, and this hopefully eliminate this problem. It creates some minimal input resistance to be seen by this noise and the undesirable signal. So this one here is a practical op-amp integrator. They put this input resistance here, and they add this resistance as well to balance the what's called the bias current. We wouldn't have to worry about that, simply one other non-ideality of the op-amp. But the most important thing to remember, when you have a very high frequency signal, it's noise signal, the gain will be equal to minus RF over Rn, is not equal to infinity. The gain will not be equal to infinity, which is a problem for the ideal differentiator. Okay, I left this slide intentionally empty so that I can show you how to calculate the transfer function for this circuit. This circuit here is a practical differentiator. So we added this resistor Rn in the beginning, and I will not, this resistor here, this one here does not really add much to me if I assume it's an ideal op-amp, because if this is ground, there is no current flowing here, then this is also ground. So this resistor really does not get into our analysis assuming an ideal op-amp. If I assume a practical op-amp, there will be some bias current, and this bias current is what's used here to we use this resistance to cancel its effect. So now let's analyze this circuit. Again, it's this one I will assume it's short circuit because this resistor does not add much. The ratio here V out over Vn is minus Z2 over Z1. Okay, so we can type that V out over V in is equal to minus Z2 over Z1, and Z1 is nothing but Rn plus 1 over SC, and Z2 is simply RF. So we can type that here. We can say that this ratio is equal to minus RF over Rn plus 1 over SC. Okay, so if you multiply both sides by SC, we end up by this ratio that V out over V in will be equal to minus RF multiplied by SC divided plus 1 plus Rn multiplied by SC. Okay, now let's multiply both sides by this term, okay, and then I will take it back from the frequency domain to the time domain. 1 multiplied by V out, if I take it back to the time domain, I get V out of t. S1 multiplies V out gives you V out dot. S1 multiplies V in gives you V in dot. So this equation can be written in this form, that V out plus RNC V out dot is equal to minus RFC V in dot. Okay, now this, for this circuit to be a differentiator, V output must be equal to the derivative of V in. So this term here is an error, term. Okay, and in order to guarantee that this error term does not interfere with the operation of the circuit, we select Rn to be small enough. So this term is extremely small relative to this term, and then we can cancel out this term. So we put Rn here just to eliminate the high frequency noise, but we select its value to be very small relative to this term here, so that it does not affect the differentiation functionality of this op-amp. So effectively, V out is equal to minus RFC V in. Okay, let's take a look at one example here. This is a differentiator. We have an ideal differentiator. We have a capacitor of 1 microfarad. We have a 10K resistor. We have what is V out here. V in is simply a triangular waveform of this form. It goes from 5 volts to 0 in 10 milliseconds, and then goes from 0 up to 5 volts in another 10 milliseconds. We would like to determine the output waveform for the shown circuit. Now, again, we apply the very simple rule that the current flowing here is the current flowing here. The current flowing through the capacitor is simply equal to C dV by dt. Okay, so the derivative dV by dt is simply the derivative of this waveform or its slope. So the slope here is positive. It is 5 over 10 milliseconds, so it's equal to 500 volts per second. The slope here is negative. Okay, actually here is negative, the slope here is positive. So here it's minus 500 volts per second, here it's 500 volts per second. And this is what we're going to be using in our calculation of the current. Once I know this current will continue in the resistor, and the output is equal to minus the value of this current multiplied by 10K. And it should be clear to you why I assume that, because if the current is flowing this way, it creates a polarity of this form, but this polarity is equal to minus V out, because this is ground. Okay, so just remember here that the slope here is negative, is minus 500 volts per second, and the slope here is positive. And the current flowing here is simply C dV by dt, or C multiplied by the slope. Okay, so we apply this equation. The current this current I1, which is the capacitor voltage, is C dV by dt. From the triangular waveform in the first part, I have 5 divided by 10 milliseconds. So the slope is 500 volt per second, and of course I have to take into account the negative sign here. So the slope is either 500 volts per second or minus 500 volts per second, depending on what part I am in this waveform. So you can see I'm saying that the slope is either it's plus or minus 500 C, so if I multiply this is C is 1 microfarad, you multiply by 500, you get 0.5 milliampere. So the current going through the capacitor is either 0.5 milliampere in this direction, or 0.5 milliampere in this direction. Okay, when the wave is going down, the waveform is going down, then the current is negative. Okay, then the current is negative and is flowing in this direction. Okay, now we take this this expression here and we substitute it in V out. We know the value of the current. The output waveform will simply equal to the current I multiplied by the 10K. So it will be I multiplied by 10K here, and this will give you the value of this output voltage. So we take V out is minus I2 multiplied by R, which is minus I1 multiplied by R. There are two currents, either it's positive 0.5 milliampere or negative 0.5 milliampere. So there is why you have this waveform that you are seeing here. So this is the output waveform that you get when the slope is negative. Okay, then the current in the capacitor is negative, then the output voltage is positive. Actually, if you do the multiplication, you get 0.5 milliampere by 10K, you get minus or plus 5 volt. And you can see here minus or plus. I used it for the current plus or minus because there is a negative sign here. So here in this part, negative slope, then positive output. Here, positive slope, then negative output, and so on. And then it repeats itself. So you can use this one to create a square waveform from a triangular waveform. And this circuit here is an example of a differentiator.